So, good afternoon, everyone, and welcome to today's QU-ATTO webinar. It is my pleasure to introduce today's speaker, Dr. David Busto. David will have a talk about attosecond time delay in photoionization. Currently, David is an assistant professor at LUND University and a VACT fellow. His research focuses on photoionization dynamics in atoms and molecules using attosecond photoelectron interferometry, as well as on developing new protocols for quantum state tomography, such as polycracking or rainbow cracking as an example. And now a little bit of history about David's scientific journey. David studied physics and chemistry at Aix-Marseille University, where he completed his bachelor's degree and first year of master's studies. He then specialized in lasers, optics, and matter at Paris-Saclay University. He continued his academic career at Lund University, where he obtained his PhD in attosecond physics under the supervision of Professor Anne Lullier, Dr. Matthew Geisenberg, and Dr. Markus Dahlström. His doctoral research focused on quantum interference effects in attosecond photoionization dynamics. After completing his PhD, David worked as a postdoctoral researcher at the University of Freiburg, focusing on photoelectron photoion coincidence spectroscopy. He then returned to Lund University, where he continued his work on attosecond quantum state tomography of photoelectrons. Welcome, David.
Thank you for the introduction. Let me share my screen. All right. Do you see my screen and the pointer and everything? Yeah.
Yes, perfect.
Yeah. So thanks, Victoria, for the introduction. Feel free to interrupt me at any point if you have questions during my talk, or just or you can also keep them for the end. So as Victoria said, today I'm going to be talking about attosecond photoionization time delays. But before diving into the topic, let me just say a few words about what I'm not going to talk about, because this is a very, very broad topic. So I am not going to talk at all about tunneling time delays. This is a very hot topic, and you could have a whole session on this. This is not at all what I'm going to be talking about. I will talk about photoionization time delay. So when you have a single XUV photon that is absorbed and creates a photoelectron wave packet in the continuum. And then I will only discuss the case of non-resonant photoionization dynamics in atoms. Okay, so this is very specific, but I thought it would be better to maybe try to dive a little bit deeper and make sure that you understand what are the basics in atoms. And then I will have a little bit of literature at the end if you're interested in the broader research that is done on attosecond photoionization time delays. So before we start, maybe let me ask you some questions. So here I have 3 questions that I want you to think about for like 5 seconds, because I think this is very important, and you can often hear questions along these lines. So the first question is, how long does it take to promote an electron from the ground state to the ionization continuum? The second question is, how long does it take to ionize an atom or a molecule? And the third question is, how long does it take for the photoelectron to escape the atom or the molecule? And the answer to each of these 3 questions, as you will see during this presentation, is that these questions do not make sense. Okay. So for the first question, we are not going to talk at all about how long it takes for the electron. When we talk about photoionization time delays, we don't talk about how long it takes for the electron to go from the ground state to the continuum, because there is no time operator in quantum mechanics, so we cannot define such a time. And then, as we will see later on, we cannot define how long it takes for an atom or a molecule to get ionized or for the electron to escape, because the electron propagates in a Coulomb potential that has infinite range. So all of these questions are, let's say, not the right kind of questions. So hopefully by the end of this presentation, you will understand a bit better what we actually mean with photoionization time delays. And a little bit of a warning, you've probably heard questions along those lines, or you will hear questions along those lines in the Atto community, because everybody, including me, we tend sometimes to make shortcuts and talk about, how long it takes to ionize the atom. This is what we're measuring, but this is not really the actual quantity that is measured, as you will see. So before continuing, let me just start by one slide on time and quantum mechanics. So time appears in the time-dependent Schrödinger equation as a parameter, okay? So in quantum mechanics, time is not unobservable, which means that there is no operator t that if you apply it on the wave function, it would give you the time of that specific wave function. And so for this reason, we cannot calculate how long it takes, for example, for an electron to go from one state to the next, simply because there is no time operator. What we do have in quantum mechanics is time evolution operators. So if I consider my wave function at time t, this is given by my wave function at t equals 0, where I apply my time evolution operator until I propagate it to time t. And in the case where I have a closed system, then this time evolution operator can be written like this. So if I quote here a sentence here from this review from Mackay and coworkers, regarding the quantum mechanical description of an energy conservative system, which means like a closed system, time enters the expression of the wave function through a phase-dependent term. This implies that time delays are directly linked to phase shifts. And so this whole business of measuring photoionization time delays, it's all about measuring the phase of the photoelectron and how it varies with energy. But before we start by discussing photoionization time delays and scattering in the Coulomb potential, let me start with discussing time delays for optical pulses very quickly. So imagine that you have a pulse that goes and propagates through some material with refractive index n. Essentially, after going through the material, the pulse will have acquired a spectral phase, which is simply given by this equation, where omega is the angular frequency, c the speed of light, l the length of the medium, and n the refractive index. What we can then do is that we can compare this compared to a reference pulse that would have propagated in vacuum. And so this means that now the pulse that propagates here through the material has acquired an additional phase shift that is given by this equation here. And so in the end, what happens is that we will get a delay between the two pulses, which is simply given by the first spectral derivative of this phase shift. And so we can do the same thing now, not with optical pulses, but with matter wave pulses. And this is what is called scattering delays. So this was initially introduced in the 50s and the 60s. And the idea is that if you have a wave packet that propagates in a short range potential, and you compare this to a wave packet that would be propagating in vacuum, these two wave packets initially are in phase, but then as this wave packet enters in this potential, the frequency, let's say instantaneous frequency and the instantaneous momentum of this wave packet will change a little bit. And then in the end, this will lead to a phase shift compared to the reference wave packet that propagated in vacuum. And so in the exact same way that we introduced the delay between the two optical pulses, here we will get a delay between the two electron wave packets, or two particles, which is given by the spectral derivative of, by the energy derivative of this scattering phase that was acquired by propagating in the potential. And we have a factor 2 because this is a full scattering event, while in our case, we're going to be talking about photoionization, which is a half scattering process because we create the wave packet here in the center, and then the wave packet only experiences half of the potential. So we can define the scattering delay in the same way, this Wigner delay or Eisenbud-Wigner-Smith delay. The only difference is that here we have a factor 2, while here we don't have this factor 2. So why is it interesting to measure these photoionization time delays? Well, as you saw from the previous animation, these photoionization time delays, they essentially probe the ionic potential. So they will probe the universal Coulomb potential, but they will also probe the short range potential, which is very sensitive to electron correlations. So for example, here you see theoretical calculations of the photoionization time delays you expect in argon in the vicinity of the so-called Cooper minimum for the 3s electron. And you can see that these are all different levels of theory. And you can see that depending on which theory you use, you can get completely different delays. And the reason for that is because all of these different models or theories account for electron correlations to various degrees. And so for this reason, this measurement of photoionization time delays is really interesting because it provides a very stringent test of the different theoretical models that are used. And so in the context of this, for example, photoionization time delays in the Cooper minimum, there was a paper in 2021 where we measured both in LUND and in Saclay photoionization time delays in argon. And in green, you see the theoretical prediction, and here you see the experiments, and you see that it didn't match at all with the theory. And it was quite puzzling for a while until finally in 2025, the group of Eva Lindroth in Stockholm was able to refine the level of theory, including additional processes, shake-up processes, additional correlation effects, and then they could reproduce this negative time delay. So this is one example where that shows really why it's interesting to do these measurements, because this provides like really really powerful measurements of these correlation effects that are not so obvious when you only look at the photoionization cross sections. And then, even though I'm not going to be talking about molecules, these photoionization time delays are also very interesting in molecules because, of course, in this case, now you start having an isotropic potential that can look very different in different directions. And so if you can measure these photoionization time delays in different directions, you can get access to how this potential looks in space and some sensitivity to the structure of the molecule. Okay, so that was for the motivation why we measure these photoionization time delays. Now I'm going to get a bit more formal and try to explain what are these photoionization time delays, what we measure and what we don't measure. So the first thing is when we describe the ionization continuum, you can describe it like this. Okay, this looks like a very big expression. What matters here in the end is just this radial wave function here. So the asymptotic radial wave function, so where we promote an electron from a bound state to the continuum, we're going to get a wave. This wave will be given at very large radial distances with this equation, where here you have a phase that depends on the position r and on the angular momentum. And this phase can be written like this. So here, the blue term, this is what is known as the scattering phase. And this is the quantity that we want to access. And this scattering phase, it has two terms. It has a universal Coulomb phase, which is the same for any particle that propagates in Coulomb potential. And then it has an additional correction that is this atom-specific or molecular-specific phase that provides all the information about the scattering delays. Then you have an additional correction here due to the centrifugal potential. That's not very important. And on top of this, you have this logarithmically diverging phase. So this means that the phase of this radial wave function will never settle to a fixed value, but it will logarithmically diverge. And so this means that there is no absolute delay of a Coulomb wave packet with respect to free propagation. So I initially showed you this example of a pulse going through a material and then pulse going through vacuum. And there we can define the delay in the precise way. We cannot do this in the case of photoionization time delays because we're propagating this infinite range Coulomb potential. So the only thing we can do is talk about a relative delay with respect to a Coulomb reference, for example, the hydrogenic system. So there are essentially two ways to measure these photoionization time delays. One is using the rabbit technique, and the other one is using the streaking technique. And in this presentation, I will essentially just focus on the rabbit technique. I think you are already familiar with both techniques. You've had some presentations from Pascal and from Yanis, so I will not describe again how this works, but instead I will focus on the rabbit technique and explain how from the rabbit technique we have access to the scattering phase. So in the rabbit scheme, we have essentially two paths. We have the absorption path where we absorb one harmonic and one infrared photon, and we have the emission path where we absorb the next harmonic and emit an infrared photon. So the sideband intensity is given as a function of delay and energy according to this equation where we just sum coherently these two paths and take the modulus square. So if I expand this like Pascal did it in his presentation, then you will see that this transition amplitude, it has a term that corresponds to the harmonics and the phase of the harmonic. Then you have the term corresponding to the electric field and the phase of the electric field, which is connected to the delay. And then you have this matrix element that describes the two-photon photonization process. And then you have the same thing for the emission term. So then if I rewrite this, essentially what I will get is I will get a constant term here, which corresponds to the modulus square of the absorption path and the emission path transition amplitudes. And then I will get this interference term where the phase of this cosine can be separated into a contribution that depends on the phase of the relative phase between the harmonics. That's the so-called Attosecond chirp, and then the phase or the phase difference of the two photon transitions, which is what we call the atomic phase, and this is what we're interested in this presentation. So if we want to know exactly what information is hidden here, then we have to look a little bit at the expression of these two photon transition matrix elements, and this is how they look like. So essentially, what this is saying is that we need to sum or integrate over all paths that go from the ground state via an intermediate state all the way to the final state. And just for information, because usually we always just plot this, but this expression also says that in principle, we also have to account for these kind of paths where the infrared is absorbed first. Now, because especially in atoms, in molecules, it can get a bit more complicated, but in atoms, usually this first process is not resonant. So if we just absorb the IR or emit the IR first, this is non-resonant. This is the amplitude of these paths is usually negligible. But if you're a theorist and you want to calculate the phase of these two photon transition matrix elements, then usually it can be important to account for these processes as well. But in the rest of the presentation, I will just completely forget about these paths and only consider these two paths. So if I take this two photon transition matrix element, then what we can do, because this is the two photon transition matrix element to get an electron with momentum case pointing in a specific direction. Now what we can do is that we can do what is called the partial wave expansion. So we rewrite this in terms of the spherical harmonics. So this matrix element now we decompose into a sum of matrix elements corresponding to different angular momentum channels. So if you remember atomic physics from if you start here with an angular momentum L, when you absorb a linearly polarized photon, you can increase angular momentum by plus or minus 1, and you will keep the magnetic quantum number delta m equal to, the same. So here, for example, if we start from P state, when we absorb an infrared, an XUV photon, we can either go from P to a D continuum or to an S continuum. And then when we further absorb or emit an infrared photon, we will change again angular momentum, going here from S to P. From D, we can go to P or to F. And so now we have to consider now all of these possible transitions, not just two, in order to describe the rabbit process. And for each of these paths here, we will get a two photon transition matrix element, which is defined by the magnetic quantum number, the intermediate angular momentum lambda, and the final angular momentum L. And each of these two photon transition matrix elements are given by the phase of these matrix elements is given by this. So here you have just like a constant term that comes from perturbation theory. Then here you have a term that depends on the intermediate angular momentum lambda. Here you have this scattering phase, which is what we're interested in, where plus means the scattering phase in the absorption process, so the lower one, and minus means the scattering phase, the intermediate scattering phase in the emission process, so the upper case. And then we have an additional phase here that appears, which is what we call the continuum phase. And this continuum phase depends on in principle, depends both on the intermediate and final angular momentum. And it's induced by the transition between the continuum states in the Coulomb tail of the potential. And I don't have time here to explain why in detail, but now you can notice that while in the first case, while we're looking at just a single continuum wave, we had this logarithmic divergence that prevents us from determining what is the actual phase. Here, when we look at the phase of the two photon transition matrix elements, we don't have this logarithmic divergence. So we can, in principle, extract this phase using measurements. So the first thing that we're going to do, because this is a quite complicated process, is we're going to simplify it first to just the case where we have a single channel. So we can forget about all of these angular momenta. And so essentially now our sideband intensity is given by this. So we have again these constant terms here that come from the modulus square of the absorption and emission transition amplitudes. And then we have the transition, the interference term here that where we have the phase difference that appears between the harmonics, between the scattering phases, and between these continuum phases. So now this, in principle, we can rewrite like this, where we have factored out omega, 2 omega, sorry, so that now we can rewrite these phase differences in terms of delays, which are defined like this. So we saw at the beginning that we defined these delays as the energy derivative of the spectral phase. And so this difference here divided by 2 omega is sort of the finite approximation of an energy derivative. And so these are more or less the same delays that we're trying to measure, where we have here the group delay of the the group delay dispersion of the XUV pulse. Then here we have the Wigner delay, so the delay associated to just scattering in the potential, and then we have now an additional delay, which is the continuum delay, which is induced by this interaction with the IR field. And usually, experimentally, as you will see, what we access is this the sum of these two delays, which we call the atomic delay. So now if we look at the case that is a little bit more complicated in the helium case, now we have one intermediate state here. So we go from 1s2 to a p continuum. And then when we further absorb or emit an infrared photon, we can either go to an s continuum or to a d continuum. So now in this case, the sideband intensity is written like this, where here we have the absorption process to the Y00, so to the S wave, the emission process to the S wave, here in red, and then in blue we have the absorption path to the D wave and the emission path to the D wave. So then what we can do is we can expand this, and so we will get a term here, which is the modular square of this term going to the S wave, this term, which is the modular square of the path going to the D wave, and then we have cross terms between the S and the D waves. And the first thing we're going to look at is when we do angle integrated measurements. So if we do angle integrated measurements, it means that we're averaging the electrons that are emitting in all directions. So essentially what we're doing is that we're integrating over theta and phi the sideband intensity. And because spherical harmonics form an orthonormal basis, essentially by integrating over theta and phi, we're going to kill here the interference term, the cross term, and we will only end up with an incoherent sum of a rabbit path going to the S wave and the rabbit path going to the D wave. So essentially what this is telling us is that now we're not just measuring one rabbit trace, but we're essentially measuring two rabbit traces that are on top of each other, one going to the S wave and one going to the D wave. So essentially, we can rewrite now our interference pattern like something like this. We have a constant term, and then we have oscillations associated to going to the S wave and oscillations going to the D wave. Now, because in both cases, we go to the same intermediate case, in intermediate state, the Wigner delay here is the same, whether we go to the S or to the D wave, but potentially we have this tau cc, this continuum delay that could be different when we go to the S wave or when we go to the D wave. So then what we can do is we can have a look at this theoretically. And so here I'm plotting these continuum delays for various atoms, helium, neon, argon, and krypton, starting from different shells. So going from P to S, S to P, D to P, D to F, even F to G. And what you can see is that all of these delays, in every single case, they all fall more or less on the same curve here, where the where the blue shaded area is an area of plus minus 10 attoseconds. So you see that there is some sort of universal behavior of this continuum delay, which is independent of the angular momentum and independent of uh, the atom. And then what we can do then is, if you look at this paper, there is an analytical formula for this continuum delay. I don't want to put it here. If you're interested, you can have a look here. And this is what I'm showing here in gray. And you can see that this analytical expression falls perfectly here on top of all these points. So what this is saying is that there is a universal continuum delay, and that we have an analytical expression so that it can be calculated. And so this is good news, because this means that if now we go back to this expression, this means that this continuum delay is the same in both cases, and that then when we measure the total phase, we will have the Wigner delay plus this continuum delay, and then we can calculate this continuum delay analytically, and so we can access this Wigner delay, which is the quantity that we're interested in. So here in helium, this shows that the rabbit technique really can access these Wigner delays. One thing that I also want to emphasize, because I guess some of you might be working on molecules or more complicated cases, this universal behavior of the continuum delay is exclusively valid for atoms. So you can't extrapolate this to more complicated systems, because it will break down. But in atoms, there is this universal behavior where it doesn't matter which atom you're looking at, doesn't matter which angular momentum path you're taking, you will have this universal delay. Now, if we look at the more complicated case here, for example, ionizing from the 2p shell of neon, now we have a lot more angular momentum paths that we need to take into account. So here we have going to the P wave, the absorption path. We can go to the S wave and then to P, or we can go to D and to P. So these are the two paths here. Then we have the same thing for the emission path, and then we can go to the D wave. This is in the case where we have M equals 0, so magnetic quantum number equals 0, but we can also remove an electron where the magnetic quantum is plus or minus 1. So on top of this, we have to add incoherently these additional terms that come from the contribution of M equal plus minus 1. So now what do we see? Sorry, so if now we take this and then we do the angle integrated measurements, what we will end up with sideband signal that will look like this. So what we see now, it's a little bit different from what we had before, because here when we look at the contribution to the P wave, where when M is equal to 0, you see that now we have two paths that add coherently. So we can go from S to P or from D to P, and these two paths add coherently, so we will have additional interference that we did not have in the case of helium. And then on top of that, we have these additional rabbit traces for going to P or for going to F when M is equal to plus minus 1. So now this means that now we have a little bit like in helium, we have now an incoherent sum of rabbit traces for the P and the F waves, but now we don't have just two traces, now we have 4 different rabbit traces that are on top of each other. And unfortunately, in this case, all these rabbit traces will not be the same. So if you look at the amplitude and the phase of these rabbit traces individually, they will be a little bit different. So in the end, what we measure is an effective sideband oscillation. And from this, we can extract an effective delay, tau A. But this is different from this it will not allow us to access these Wigner delays of the S and the D waves. So they will be mixed together, and experimentally there is no way you can separate it. So either you ask theorists to help you and try to extract what are the different Wigner delays, or you need to do better measurements, which are angle integrated, angle resolved measurements, which is what we will talk about in a second. So what this means is that in general, it's not possible to extract exactly the Wigner time delays from angle integrated measurements if you have if you start from a shell that has angular momentum equal to 1 or larger. I see there's a question from Carlo. Yes.
Well, the question is if you can use polarization to separate a little bit these contributions.
Yes, absolutely. You can use polarization, and the fact that the selection rules are different for circularly polarized light, or if you have pulses that have orthogonal polarization. This is not at all something I will talk about now, but if you can end up in a situation like in helium, where you only have one intermediate continuum, then you can fall back on the previous case, and then you can extract the Wigner delay. So yes, it is possible to use something else than just two linearly polarized pulses, but I don't have time to talk about it here. So just an example about on how you do this time delay measurements from angle integrated time delay measurements. So this is measurements that were done, some of the first rabbit measurements that were done in argon, measuring the time delays, and they were ionizing from the 3p shell. And so now your Simon signal will look like something like this, where now you have two contributions. You have the Atto chirp contribution, and you have the contribution of this atomic delay from the 3p shell. If you have enough photon energy, you can at the same time also ionize from the 3s shell. And now the trick is that because the Atto chirp is the same, because it's the exact same attosecond pulse train that is used, if now you start measuring the delay difference between these two, then you can access what is the delay difference between electrons escaping from the 3s shell and from the 3p shell. And this is what they measured in this paper in 2011, where you can see here that the delay is of the order of a few tens of attoseconds. And this value of this delay, then you can compare to theory, you can compare to different theoretical models, and you can learn more about the role of electron correlations in this process. You can also do this using the streaking technique. Again, I will not go into detail about how this works, but the idea is the same. You need to ionize from two different shells. So here, the first experiment were done in 2010 in neon, ionizing from 2p and from 2s. And they could extract these two streaking traces for the 2s electron here at lower kinetic energy and for the 2p electron at higher kinetic energy. And then when you use your retrieval algorithm, you can extract a delay between the 2s and the 2p electrons, which in this case was of the order, they measured something of the order of 20 attoseconds between the 2s and the 2p. What is interesting also is that despite rabbit and streaking being fundamentally different, rabbit is perturbative. It uses an attosecond pulse train and a long infrared pulse. Streaking uses an isolated attosecond pulse, a strong infrared pulse. It's almost classical in a sense. In this review paper, they compare theoretically the time delays extracted from rabbit and streaking, and they show that essentially these two techniques give the exact same results. So it doesn't matter whether you use rabbit or streaking, you will get the same result. And what's even more interesting is that they showed that the distortion from the infrared, both in rabbit and streaking, are exactly the same. So here you see this continuum delay, which are the dashed lines here. And then the solid lines are what they call the Coulomb laser coupling. This is how they call this IR-induced distortion in streaking. And you can see that despite being two very different techniques, this distortion from the IR field seems to be the same in both cases, because it is really linked to just an electron propagating in a Coulomb potential under the influence of an external magnetic field. Good. So this was for angle integrated measurements. Now we'll quickly talk about angle resolved measurements. If we go back to helium, we have this situation here where now we really have four paths: absorption to the S, emission to the S, and absorption to P, and emission to P. So one thing that we can do, for example, is group the paths going to S and the paths going to D. And then we can look at the modulus square of this signal. So what we see is that for the S, the path going to the S continuum, it oscillates, and the same for the path going to D as a function of delay. But in the case of D, we see that it doesn't go all the way down, while for S, it does decrease a lot more. And the reason for this is that when you absorb an infrared photon in the continuum, you can either absorb or emit, you can either increase or decrease angular momentum. This is what selection rules tells us. But you have on top of these propensity rules, with Fano's propensity rules, that tell you whether you're more likely to increase angular momentum or decrease angular momentum. So both options are still possible. But for example, in the case of absorption, you will tend to increase angular momentum, while in the case of emission, you will tend to decrease angular momentum. And what you also see here is that the asymmetry between absorbing or emitting an infrared photon, when you increase or decrease angular momentum, increases where you go to higher angular momenta. So if now we use this and we look back at this rabbit process, what it means is that in the absorption path, we tend to go to the D wave, while in the emission path, we tend to go to the S wave. And this asymmetry between absorption and emission is stronger for the D wave, is stronger for high angular momenta than for low angular momenta. So now what it means is that now you have an interferometer here that is imbalanced. The two arms of your interferometer don't have the same strength. And so this means that you will end up with a reduced interference contrast. But because in the D wave, the asymmetry between absorption and emission is larger, then we end up with a reduced contrast. And this is why we get this curve here that doesn't go all the way down. What does it mean? Well, what this means is that as a function of the XUV and infrared delay, we have the angular distribution that is changing. And when you approach, so here, initially the S and the D wave have approximately the same strength, and you get this sort of P-shaped angular distribution. But then as you go here towards the minimum, the S wave really goes to zero, and then you almost get only a D wave, where you get this strong probability to get an electron emitted perpendicular to the laser polarization, which is in this direction. Alternatively, you can take this equation and now, instead of grouping it according to the partial wave that you're reaching, you can group it where you have here the absorption path and here the emission path. So in this case, now what happens is that if we rewrite the sideband intensity, we will get something like this. We will get a term that is constant, that is independent of delay, that corresponds to D plus, to the modulus of D plus squared plus D minus squared. So this gives you like an angular distribution that is fixed. And then on top of this, you will have a modulation now, which depends on the emission angle, which comes from the cross term the interference between these two terms, and we will get an atomic delay, which will depend on theta and phi. So what you can do is that you can separate the absorption and the emission processes and look at the amplitude and phase, or here in this case is just the phase divided by 2 omega. And what we see is that in the emission case, we have this, this minimum here that doesn't go very deep, and we see that the corresponding delay here doesn't vary a lot. In contrast, in the absorption path, where the D wave is stronger than the S wave, then here we see that we get this very strong destructive interference. And at the position of the destructive interference as a function of angle, you get this large delay variation. So now, since in the rabbit technique, we measure the difference in phase or the difference in delay, now we measure the difference between this phase variation here and this phase variation here. That gives us this delay here as a function of emission angle. And so what this means is that this phase variation here really comes from the fact that we have an asymmetry between the absorption and emission processes. Because if both in absorption and emission we had the same probability to go to S and D, we would get a delay. We would get a phase or a delay that depends on angle, but it would be the same in the absorption and the emission paths. And so in the end, when you measure the difference, you would get 0. But here, because of this asymmetry, we get this phase variation or this delay variation that has been observed. So if we want to dive a little bit more into where exactly this comes from, so this really comes from the matrix elements, which take this expression. So I'm going a little bit faster now because I see that I'm out of time. But the idea is that you can take these matrix elements and you can expand it with all the phases that we did before. So for the S and for the D, we write it like this. And so for the S wave, we will get this term here for the absorption and emission path. And then for the D wave, we will get this term here. So what you see is that essentially you have an amplitude here, which is what it is. And then the phase, which is almost the same in both cases for S and D, except for this continuum phase. So what you do is you can factorize this the phase that is the same in both terms, and then you get a second, and then this is multiplying this interference part between the S and the D waves. And so if now you extract the phase from this, what you will get is the phase of this term plus the phase of this term. And now what is interesting is that here you can see that this global phase, which is the phase that contains the scattering phase, which is the term that contains the scattering phases, the intermediate scattering phases, it does not have any spherical harmonic attached to it. So this means that here we have a completely isotropic Wigner delay. And the fact that we measure this delay variation, this really comes from the IR-induced transition, which is angle dependent. Now, I haven't written this as tau CC for a reason, because here this delta phi CC is not universal, because it depends both on these continuum phases and on the two photon transition amplitudes. And these continuum phases, they are actually universal, so they are the same for all the atoms. But these two photon transition amplitudes, they vary a lot as a function of the atom, as a function of the angular momenta, which means that this distortion here, angular momentum, angle dependent distortion, is completely different for different atoms. And so I just want to finish by giving a few examples of what has been done regarding the measurement of photoionization time delays. So the first measurements, as I mentioned, were by Schultz and co-workers using the streaking technique, where they measured a delay of 21 plus minus 5 attoseconds. And these measurements were a bit of a problem at the time because they couldn't be reproduced theoretically. So here you see a figure where you have a lot of different theoretical models, and none of them were able to reproduce these measurements. And so people were a little bit worried because if this doesn't work in neon, then there is no point in trying to go to more complicated atoms or molecules. But then in 2017, we did some measurements, this time using the rabbit technique. So exactly the same thing. There's a typo here. This is the rabbit scan from the 2p shell of neon and from the 2s shell of neon. And because in rabbit you use attosecond pulse trains, you have harmonics which are spectrally narrower. This allows you to get higher spectral resolution. And so what we observed in the signal was that there was a little bit of contamination here from additional processes known as shake-up. So these are additional ionization processes that have a different phase and that are polluting a little bit your signal. So just like in the previous case, you are essentially adding two rabbit scans that have different phases on top of each other. And so if you're not careful, when you extract the phase, you will get a phase that is not well reproduced by theory. But in this case, because we could separate these different processes, you can see that these are the measurements that we obtained, and they were in very good agreement with theoretical calculations. And this is the famous measurement by Schulze and co-workers, where because they were using isolated attosecond pulses, they couldn't resolve these different processes. And so they had a little bit of this contamination from shakeup. And here, this shows what you get once you subtract this continuum delay. And you see that in this case, essentially, the Wigner delay was very, very small, close to 0 attoseconds. Then the first angle resolved measurements, they were in 2016, where essentially they were measuring rabbit traces for electrons emitted at different angles. So here you see electrons emitted in between 0 and 30 degrees with respect to the laser polarization, here between 60 and 65 degrees. And for every single case here, they could extract the oscillations and measure the delay. And so they observed this very strong angle-dependent delay that comes, as we discussed, from the infrared probe. And then you can do the same thing here for more complicated situations, for example, in argon, where now you have a lot more partial waves. I won't go into the detail, but essentially you can do the same thing. You can extract the delays and compare to theory, and you see here that we have very good agreement. And then the last example that I want to show is measurements that we did in neon. Again, angle resolved measurements, where we measured how how these the different sidebands evolve as a function of as a function of delay and as a function of angle. And long story short, you can go and you can fit the angular distributions according to these very complicated equations, where you use the fact that these continuum transitions are universal. They're the same for all the atoms, and you can calculate this analytically. And like this, we were able to extract now these Wigner delays associated to the different shells. So here going to the S state or going to the D state. So to summarize, the conclusion is like it's that it's all about phases, and sometimes I wish that we talked a bit less about delays and more about phases, because When you talk about delays, it only works in very specific cases, but if you talk about phases, this is always valid. If you want to talk about photonization time delays, you always need to reference it to a Coulomb reference. And these photonization time delays or phases, they are very sensitive to the propagation of the photoelectron, the ionic potential, and so they provide a lot of information on the correlations. We also saw that the IR probe introduces distortions, but that these are universal, so we can correct them in atoms, not other systems. And in angle integrated measurements, you essentially end up in most cases by averaging incoherently different kind of rabbit measurements. So it's difficult to extract what are the relative phases between the different partial waves. While if you do angle resolved measurements, you get a lot more information about the interference between the different partial waves, and then you can extract how these delays or phases vary for different partial waves. And so if you're interested to go beyond this, there's a lot more work that has been done in atoms, looking, for example, in the case where you have resonances close to the intermediate or final state. So here are some references. In the case, as Carlo hinted, where you use, for example, different kind of polarizations, not necessarily just linearly polarized light. And here as well, some references on photonization dynamics in molecules, and there's a lot more. So I'm sorry if I didn't cite your favorite paper, but it's really impossible to cover the whole field. And these are the references that I used when I prepared this presentation. And finally, I would like to thank the group here in Lund, and in particular, all of these people with whom I have worked for many years on this measurement of photonization time delays. And I thank you for your attention.
Thank you, David, for a very nice talk. Now we have some time for questions. Okay, we have a lot of applauses. Very nice. Yes, Carlo?
It's actually not a question, just a comment. Among the interesting connections of phase or time delays with something else, Anatoly Kayfets is proposing that there are Kramers-Kronig type of dispersion relationship between these and the cross sections.
Yes, and there are indeed connections, but I think they also show that they have phase ambiguity problem, sign ambiguity problem. And so, for example, in the case where that I was showing, maybe I can skip. Here, for example, in this Wigner delays close to the Cooper minimum, there was a disagreement between different theories whether the delay should be positive or negative, and this Kramers-Kronig relation does not allow you to solve that problem. So you still have this sign ambiguity problem. There is a recent paper from him and Hans Jakob Werner where they discuss about this. More questions? Everybody's hungry.
Yes, Yanis? Oh, Juliana. There is a question.
Mine is quick. So David,
Okay.
you saw the Wigner is isotropic in helium, but this does not apply for neon, right?
No, exactly. Yeah. So in helium is isotropic because you have a single intermediate partial wave. So even though the spherical harmonic Y10 is not isotropic, the phase is the same regardless of the direction you're looking at. So the Wigner delay is isotropic. But of course, if you look at more complicated cases like here, where you go to different partial waves, then it will not be isotropic, because then you get the interference between the two partial waves. There was another question before.
Yes, from Juliana. Do you still have a question?
Yes. Can you hear me now?
Yes.
Because my internet connection got lost. Yeah. Just a quick question, simple one, because all of these examples that you gave were about atoms. How much complexity would be introduced if we looked into like some small molecules?
So the answer is a lot of complexity. So I guess you saw that already just in neon or argon, it's quite complicated. So it gets a lot more complicated to the point where you cannot really, or it becomes very difficult to have this approach where you really go and isolate the different partial waves. But that doesn't mean that you can still learn a lot. I mean, when I was a postdoc in Freiburg, we did a lot of rabbit measurements in molecules. You have to give up a little bit on the possibility to really go and understand every single aspect of it. But then in collaboration with theorists, you can really go and try to understand why the phase is varying in this direction, in that direction, at this specific energy, and these kind of things. You also have to start taking into account that, of course, the molecules are vibrating. So potentially you can start coupling electronic and nuclear degrees of freedom, which is very important and is very difficult to take into account theoretically. But again, these measurements provide very good tests for theoretical calculations to see if they can really reproduce the delays that are measured.
Okay, thank you.
I have a question.
Mm-hmm.
In the recent experiments we did, we saw some argon 2 plus channel, and there also we see some kind of not a Cooper minimum, but a phase change. So are there any studies for argon 2 plus?
To my knowledge, no. I mean, there's a lot of studies on atoms, but for the vast majority, these are really from ionizing the valence shells. So 2s and 2p, 3s and 3p. So there's not a lot of work on ionizing deeper, or on the case where you have double ionization and these kind of things. There are a few works, but very little. So there's still quite a lot to do in atoms. But the general formalism, yes,
it shows a similar kind of as argon 3s.
Yeah, I mean, I cannot comment on a specific case. I'm not sure. Yeah, I would have to look more into the detail. But essentially, the formalism that I presented here is valid also in the case where you have multiple ionization. So in the case of double ionization of argon and these kind of things. So then if you see the same phase variation, then essentially this is saying that the electron correlations that we see in the 3s also, or in the 3p also appear in the doubly ionized argon.
But there's no theoretical calculation done so far on this.
Not to my knowledge, but it could be. I don't know. I don't know all the papers.
Okay.
Okay, do we have more questions? It seems like not. Yanis, maybe then we can stop recording and see if we have questions of shy people.
Yes, of course.